and welcome. This video is about bit banging the I2C data bus for use with small micros that don't have an I2C bus built in. One of the things you need to understand about the I2C bus is it is an open drain or open collector output. And so there is nothing connecting the internal part of the chip to these lines that pull the signal high. The lines are all pulled high by their pull-up resistors, hence called pull-up. The open drain setup may only pull the bus low or release it and let the resistor pull it high. The logic part of it wants to pull it down. It will activate the FET transistor, and that will provide the shorting path to pull the line low. When you want it to go high, the slave or the master releases the FET or the transistor by turning it off, and these resistors will then pull the bus high. The lower the capacitance on the bus, the higher the value you can have. It's just you need to pull that high enough in the required time. Now, what's the problem with bit banging? Well, if we look at the bit banging, this is what an I2 device looks like. It has an pin to the outside world, be it the clock or the data, and we pull it up to VCC. Internally, it has an input that can monitor the voltage on that point, and it has a method of turning the FET on, which pulls current down here and makes it go low. When you release that FET, current stops flowing, that resistor pulls it high. Now, this is a very simplified drawing of a microcontroller input. There's going to be a lot more stuff on here, especially like the AT-Tiny, where you've got active pull-ups and things like that. But this is just simplified so that basically when you're using it as an output, you can ignore that. And then basically when you set the output low, this FET turns on, output comes low. And when you want to pull it high, this FET turns on, output gets pulled high. This isn't what we want, so it gives us problems. So we have to work around it. And one of the ways of working around it is to effectively use the microcontroller itself to alter the circuit here. And so effectively what we use is the direction mode register, the control register, the one that tells you whether it's an input or an output. That way, if we want the pin to go low, we set the output or the pin to an output, and we have a low or a 0 in that bit for that pin loaded in the register. So as soon as you set it to an output, that pin goes low. Current flows down here through our pull-up resistor, down through the FET to ground, and we pull the output pin, we pull the pin low, giving us the low. Now, if we switched it to a high, we would pull that up and effectively short out that. And that doesn't meet the requirements of being open drain or open collector. But what we can do is we can switch it to an input. And by switching it to an input, effectively we disconnect these two FETs from the circuit, and effectively we have a high impedance because it's an input. So when we switch to an input, that resistor, there will be no more current flowing in here, so that resistor will pull the pin high. And we achieve that. And the way we go around it is, instead of going pin high, pin low, we have a bit of test code. And if you look at the test code, we're setting pin 6 as an output. And then in this loop, we are setting pin 7 as an output, and that will pull the pin low. And we're setting pin high, so that will go high. Then we are setting port 2 or pin 7 as an input, and that will make the pin high impedance, and so it will pull up via the resistor and go high. And then here we're setting the pin low. So if you monitor those two pins when this program runs, you should see an inversion going on, and I'll show you that now. So looking at the scope here, we can see pin 7 going low because it's been turned to an output. Here we see pin 6 being set low, so it's coming down. Here we see pin 7 being set to an input, and the external resistor is pulling the level back up. You see it's not as fast a rise time. And then we see pin 6 being set high. So that is a digital output going high, low, high, low. This is a digital output being changed from an output to an input, output to an input, output to an input. I think if you speed it up, you will see that because it's a resistor pulling it up compared to an active device, we are seeing a difference in the rise times. And then thing to notice, if I take the resistor off the pin, it drops down considerably because it's no longer being pulled up. And if I bring the camera over to look at it on the board, if I connect a little LED and a resistor between 0 volts and pin 7, you see nothing's happening. But if I connect VCC via the diode and resistor to pin 7, we can see the diode lights up because it is in fact being pulled low. So that does show you that there is an active low but no active high. In part 2, we'll look at some code and we'll look at the way we need to drive it, the start condition, the stop condition, and the bits in between. Bye for now. If you like what you see, hit the subscribe button, click on the bell, and I'll catch you on the next one.